All right. So you want to skim through this lesson or do you want to just jump on in?
Well, it's polar, right? So we should just do it cold.
Ooh. You just said the joke and I asked you to do it again because it was so good. Someone in their journal said recently that they like some of our jokes and it kind of made it warmed my heart. I was like, oh,
better than nothing.
They're like, I don't like them all, but some of them are good.
I'll take that. That's high praise from a teenager, you know?
Yes. All right. Our jokes aren't, well, no, they totally are like bad. Okay, anyways, let's jump into this thing.
Our jokes are great, Mr. Kirk. Don't downplay how awesome our jokes are. We're really funny.
I got my warm coffee here because it's cold outside. Oh my God, what's that behind me?
Ah! You have a very large polar bear. I think my polar bear is not as big as yours.
But it is, but they are looking at us. They're like, what are those two people doing right now? How do they have those computers plugged in? There's no outlets here.
There's no Wi-Fi here.
And how are we talking? We don't speak English. Okay.
Anyway.
All right. So the only joke that was funny there was that first joke. Okay, so we're doing polar coordinates today. Unit 8, lesson 1. We're starting something new. New is kind of a misnomer though, because it's going to touch on many things that we've done. Polar coordinates. Let's jump into this. All right. So would you be so kind to read to us the paragraph here?
Sure, as long as you put our names on the thing. Okay. This is really important. Especially as we go back, if we're thinking about like, oh, we're going to go back into in-person school, you need to write your name on stuff because it doesn't just tag it when you turn it in. In a polar coordinate system, a fixed point O is called the pole or origin. The polar axis is a horizontal ray directed to the right from the pole. A point P is written in the form r, theta. The distance from point P to the pole is the absolute value of r. The measure of the angle formed by OP, the ray, and the polar axis is theta.
All right, let's draw this out so like it makes more sense. But I do have a big qualm with polar coordinates, and that is the order of r, theta. I think it's super counterintuitive, but you can prove me. You can tell me I'm wrong later on. I just hate that it goes r theta instead of theta r. But anyways.
Why? That's weird.
I'll explain a little bit later. Think about functions. Anyways, we have in a polar coordinate system, a fixed point O called the origin, a polar axis, which is a horizontal ray directed to the right from the pole. When you think of a ray directed right from an origin, what do you think?
That's the positive direction.
Well, it's positive, but like you can kind of think of it as the x-axis, right?
Okay, yeah.
But it's not the x-axis. It's the polar axis. The distance from point P to so we have a point. Draw a point on the screen.
I should change colors. I should make it not.
Ooh, cool. Colors. Perfect. Very nice point. Okay. So a point P is written in the form r theta. The distance from P to the pole is r. And the angle formed by OP and the polar axis is theta. The polar coordinate system is an entirely new way to describe points in space. Right? Back in the day, if I wanted to talk about that point P, I needed to figure out how far away it is horizontally from our origin and how far away vertically it is from, well, actually, how far away horizontally is it from the y-axis and how far vertically is it from the x-axis, which is all kind of based on the origin. But we can now describe points, and we've always been able to describe points using these two numbers instead. And I have a question for you. I'm going to draw a little graph on the side. I'm going to give you the point 3, 4. Can you describe that point 3, 4 with our Cartesian coordinate pair differently? Can you give me two different numbers that give me that 0.34?
Well, if we're thinking in polar, we can think about this distance, because this is what, a 3, 4, 5 triangle. So we have r is 5, and then we have this theta, which would be, is that something nice or is that not something nice? Do we need to use some trig?
Well, let's not do true. We'll save the trick for later. I guess my question is, there is only one way in the Cartesian coordinate system to describe the 0.34 in the Cartesian coordinate system.
Oh, okay.
X comma y. Okay. 3,4 is the only way to describe that point, but you're getting at what I'm trying to get at, which is there another way to describe the point r comma theta?
Is there another way to describe the 0.34 in the
Well,
form
let me do this.
of r theta?
Let me do this. Let's say I give you the point. Let's say like 3, 45 degrees, or let's better yet 3, pi over 4. So my original question was, can we describe the 0.34 differently using Cartesian coordinates? And the answer is no. A coordinate in the Cartesian system describes a point uniquely. But down here in my polar coordinate system, r comma theta, can you give me a second set of coordinates that describe that point?
Can we say, we're allowed to make r negative?
I think so. Yeah. So a negative r, what would that mean?
That means that we would need to have an opposite theta, a theta that will get us the other side.
Yeah. So
what?
We like go pi over 4 and then we
4.
go in the opposite direction. So like -3, pi over 4 is over here.
So then we would want -3, pi over 4 plus pi is 5 pi over 4 to get us back around.
Yeah. So and this is one of the reasons why I wish that the people that invented the polar coordinate system put the angle first and then the radial distance second. But what I like to think about is we go 5 pi over 4 radians, or 200 and whatever degrees. And then we go in the opposite direction of that ray, 3 units. So -3, 5 pi over 4 describes the exact same point as 3, pi over 4. Can you give me another one?
Well, we could do 3, pi over 4 plus 2 pi.
Mm-hmm. What would that be? That would be 9 pi over 4?
9 pi over 4.
Give me one more.
Could have.
Give me another one with a negative radial length. So we're going in the opposite direction.
-3, and then can we do a negative theta? -3 pi over 4?
Yeah. Ooh, that should have been there the whole time. -3 pi over 4. Yeah. All right, 4 different ways. And it doesn't stop there. We could just keep adding 2 pi to any of these. And we get the same coordinate. But that's a kind of a big deal. Not necessarily a bad thing, but something that we need to recognize. And that is the Cartesian coordinate system, you describe points uniquely. Whereas in the polar coordinate system, this new coordinate pair, 2 numbers describing a point, it's not unique. Right? You can describe the same point in multiple ways. Let's keep going. Let's get a little bit of practice. Let's graph some points. We don't have to do all of them, of course. Can you graph the point 3, 2 pi over 3?
I can. So we go out to 3, and then we go around to 2 pi over 3. So we drop a point 2 pi over 3.
So I do like, it sounds like you're thinking about the radial length first and the angle second. So.
And that's what my pushback was going to be on your argument of like angle first, because I think if you're thinking about like physical applications of this, you want to think about, I don't know, like maybe like shooting arrows and like how far you want to shoot the arrow, like how much you can pull back and then the angle that you do, right? You don't like do the angle first and then you pull back.
I've never thought of a bow and arrow being like an application of polar. I like that. Okay, so you went out 3. You're imagining this circle, I'm guessing, and then you found that angle 2π/3. Awesome. So we have on the screen here like a standard polar coordinate system that might be presented to you, but very often you'll see a Cartesian coordinate system, and you got to kind of work with polar within the Cartesian coordinate system. We'll get to that in a second. Let's do one more. Which one are you feeling? Let's do one of these double negative ones.
Yeah, let's do E because we did a vowel. We did A, so we can do E. So it's at -5. So I go to the -5 circle. And then I go -π/12. So I need to go down. So I go here.
Let's see. I haven't seen the point yet. Okay, so the way I think about it is I have a ray at -π/12, and then I go in the opposite direction of that ray 5.
Oh, so then I have this wrong. I need to move it up.
I think, yeah, you need to move it up a little bit. I have this ray at -π/12. And then I go in the opposite direction of that -5.
Okay. So then for this, it makes sense to think about the angle first and then the ray. All right.
I could see pros and cons to both.
So we're gonna leave the incorrect one.
Write incorrect on it. Bad. Not bad.
Incorrect.
Just incorrect.
Okay.
I'm so pessimistic. All right. So let me do this. Purple. And then, I don't have green.
I can do it.
You got it? Cool. Awesome. So let's proceed. So if you guys want some practice, B, C, D, and F, graph them on here. Go look at the answer key and you'll see if you got them right or not.
Sweet.
Let me scroll down. There's another. No, there's not. Never mind. All right. So we've now looked at the polar coordinate system. We've graphed some points. Back in the day when you learned the Cartesian coordinate system, you plotted some points. Now it's time to describe the first thing that you ever graphed, most likely, after points. What was the first thing you ever graphed in, I guess, algebra after you graphed your first set of points?
Graph lines.
Graph the polar equation theta equals π/4. Let's see what you got.
Okay, so π/4 is all of this in the positive side if we have positive r values. But if we have negative r values, then we also continue this. And I'm just going to push that over here where it looks like it's 5π/4, but it's still continuing on the direction of where π/4 is.
Boom.
How's that?
Theta, that's beautiful. Theta equals π/4 is the diagonal line with angle π/4 with the polar axis.
So what's the slope?
Ooh, the slope here, it doesn't appear in our line equation. One of the reasons why I like polar equations is they're very elegant. It's just a number. The slope is 1, right? Ooh, I think I can think of a way to get the slope.
Are we going to go off on a tangent now?
Oh, all right. One way I like to think about this, I'll just add this, is when I teach geometry and we're graphing vertical and horizontal lines, people tend to get like x equals a number and y equals a number mixed up. Y is horizontal, x is vertical, but people mix that up. And I like to just like write down a bunch of points whose x coordinate is that number. So if I'm graphing a line x equals 2, I just write down a bunch of points where the x is 2 comma something, 2 comma something, 2 comma 1, 2 comma -1, 2 comma 11. 11 is usually not on a 10 by 10 graph. 2 comma 3. And I graph those points and I start to see that this line is in fact vertical. I do the same thing with theta. I graph a few coordinates whose theta is π/4, 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 1, 2, -3. Right? If I had graphed these points, I would have gotten the exact same line that you you tackled. I like how you did it though.
Cool.
Is there another equation that represents the same graph?
Yeah, I think the 5 pi over 4, like if we have theta equals 5 pi over 4, or theta equals negative pi over 4, still work.
Polar coordinates, once again, it's not a bad thing, but it is something that we need to be cognizant of, and that is we can describe things in multiple ways.
Mm-hmm.
Right? How about graph the polar equation r equals 3?
Well, that means that we need to look at this 3 and just graph everywhere on it. So Kami.
Boom. Kami's the best. I'm also getting better at using the circle tool in Kami. The trick is to start, what is it? Where you, I forget the trick.
You start at the edge.
Yeah, you start at the edge and then you find your center, right?
Yeah.
Which is like counterintuitive to like other programs where you find your center and then you pull it out the radius length. Not a big fan of the choice they went with circles, but it is what it is. Cool. And when I do this, when I do the same thing as I did before, I graph a bunch of coordinates whose r value is 3 and the theta value is allowed to vary. And I would be constructing the circle that you knocked out. But one of the cool things about polar is it makes circular things really easy to describe. Do you remember the equation of a circle in Cartesian coordinates?
Oh, it was like very Pythagorean theorem-y, right?
It was like very Pythagorean theorem-y.
It was x squared plus y squared equals r squared.
Yeah. And then it gets even more complicated when you throw in like a different
you center it somewhere else.
Yeah, when you center it somewhere else.
Oof.
Right. I will say that polar coordinates, when you center your circle not at the pole, it gets a little bit more complicated, but it is still a little bit nicer than this form, right? Cartesian. Right. Polar. The polar one is a little bit simpler, if I do say so myself. R equals 3 is a circle centered at the origin. Okay, let's proceed.
Could we also describe this circle as r equals negative 3?
Absolutely. We forgot to answer that question. Is there another equation that will produce the same graph? Yes. R equals negative 3. I think that's the only other one, though.
You could do like r equals 3 plus 7 minus 7.
Well, then my whole theory that you can't do this in Cartesian kind of falls apart.
Yep. I'm just saying.
Not wrong. All right, let's proceed. All right. The graph below represents a rectangular coordinate system on top of a polar coordinate system, so that the origins coincide and the positive x-axis aligns with the polar axis. In polar coordinates, a point P is identified as r comma theta. In rectangular, a point P is identified as x comma y. What I want you to help me do is convert this point P, which is currently at 4 comma 30 degrees, 4 comma pi over 6 in polar, to rectangular coordinates, x comma y.
Okay. So there's a lot of, I guess, translation that needs to happen between like what we're thinking about. And I think maybe the easiest way to get there, given that we have spent a lot of time dealing with triangles, is to draw a triangle.
I feel like 9 times out of 10, maybe even 99 times out of 100 in math, to figure out where you're going, you draw a triangle.
At least in your class.
Yeah, I guess, yeah. You don't draw triangles in calculus all the time?
I mean, like, we draw triangles and then we think about them.
Exactly, that's what I'm saying.
All right. So let's see. How long is the what do we know about this triangle? Well, we know that the hypotenuse is going to be 4. And we know that this angle is 30 degrees, or like you translate it into radians, it's pi over 6. So now what should we do? We have a lot of trig in our pocket. So how can we use that trig to our advantage?
Let's find the x and the y coordinate.
So x equals what?
X is going to be, so when I'm thinking of the unit circle, we're not, this is a 4 unit circle. So I want to multiply this by 4.
Mm-hmm.
The X is going to be 4 cosine theta, 4 cosine pi over 6.
And then our Y.
Y is going to be 4 sine pi over 6.
That. All right.
Cosine is our X coordinate and sine is our Y coordinate on the unit circle. This is a 4 unit circle, so we're multiplying them by 4. Yeah, I feel pretty confident about that.
All right. So then can we simplify that?
I think so. I got my speed trig down. All right, cosine pi over 6 is going to be the X coordinate root 3 over 2 times 4. So
Times
2
4,
root 3.
so 2 root 3 and
sine pi over 6, that's the good one. That's Y. That's going to be 1/2 times 4, 2.
2. Okay. So there we go. We got our coordinates.
Let me zoom back out. 2 root 3, comma 2.
2 root 3, comma 2. Oh.
I think I'm gonna like do the congruent symbol.
Oh.
I don't know if that's technical, but yeah, I don't know if that's technical, but I also don't want to write equals because that would kind of imply that 4 equals 2 root 3 and 30 equals 2, which is kind of confusing. Polar. Rectangular. You know, I've been saying Cartesian this entire time. That might not be technically correct. Let's go with rectangular from here on out.
Sounds good.
Cartesian, Descartes. Cool. All right. So what did we do at the end of the day?
We drew a triangle and then we did some trig.
But like, we only used these 2 numbers the entire time, right?
Mm-hmm.
So like if I give you a comma theta, I guess r comma theta would be the smart thing to do because that's what we said. What would the Cartesian coordinate be? I did it again. Rectangular coordinate be. What did we do?
So we would have, for our x coordinate, it would be r times cosine of theta. And for our y coordinate, we would have r times sine of theta.
That's a pretty easy conversion.
Mm-hmm.
Oh, let's use it. Right. The rectangular coordinates of x comma y of a point named by the polar coordinate r comma theta can be found using trigonometry. Find the rectangular coordinates below. -2, 5 pi over 6. Let's try this formula. So r -2 cosine 5 pi over 6, comma -2 sine 5 pi over 6. Can you do me a solid?
Mm-hmm.
Would you mind simplifying those into real numbers, not trig, while I draw the coordinate -2, 5 pi over 6?
Sure. Where are you drawing so I don't?
I'm going to draw right here. Do you see it?
On the right.
Yeah,
the left.
on the left. So 5 pi over 6 is going to be like in this direction. And I'm going to go in the opposite direction, 2 units. Because the best way to check if you get it right at the end is to just graph both points and see if they're on top of each other. Ooh, I'm feeling good about this. Those negatives are going to cancel on your x coordinate. The 2's are going to cancel. √3, comma. Boom. Those feel the same. Sweet. That formula we came up with seems like it's working. Just r comma r cosine theta comma r sine theta. Let's double check it with b and then keep on moving on.
50 degrees.
-50 degrees.
-50 degrees.
Oh, we might need to break out a calculator. All right.
Yeah.
6 cosine -50 degrees, comma 6 sine -50 degrees. Are you breaking it out?
I'm getting MATLAB because my calculator still doesn't have batteries.
Love it. So we got -50, which is like down here, and we're going to go in the direction of -56. So it's going to be like kind of way down here. 50 is bigger than 45, so let me go a little bit more than halfway. I'm trying to think of something to pass the time with.
Oh, okay.
I wish I knew. Ooh. Some MATLAB code. Let me erase this these parentheses.
Let me move that up then. So we have, for MATLAB, it assumes that you're talking in radians because that's what like normal people do. So then if you're not doing radians, then you need to make it cost or sine.
Ooh. All right, so negative, so we got 3.8 and negative 4.5. Looks like we're in business. These are roughly the same coordinate. They are the same coordinate, just with my sketch, they are they're about falling on the same spot. So the only error is my bad sketch. Sweet. There we go. General set of formulas. We got it.
Yep.
R comma theta is just R cosine theta, cosine being the x coordinate on the unit circle, and then R sine theta. Boom. Polar coordinates. It is pulling from trig. The entire second semester of pre-calc seems to be pulling from trig. We did trig and then we've just not stopped using it.
You want to use your little congruent symbol so that it's like not implying that R is equal to R cosine theta.
Did you know that if you cosine theta is the multiplicative identity?
Mm-hmm.
Anyways, okay.
In Mr. Kirk's weird notation world.
Yeah. All right. So we are, so we just converted, what did we do? Polar to rectangular? Let's convert rectangular to polar. So suppose you have a given point xy. Find the polar coordinate r comma theta.
This seems more complicated. A little bit.
Yeah. Let's do it with some actual points and see what happens. So we have,
that's nice.
5 comma 12. Do you know why it's nice? Well, I know you know why it's nice.
Because you get 13.
You get 13. That is a Pythagorean triple. I was talking to someone recently about Pythagorean triples in their journal. Should we just go ahead and write 13?
Yeah.
Sweet.
Leave it as an exercise for the viewer.
Okay. So what do we need? Oh, we got 13. That's the radius, right?
So now we're just missing our angle. And maybe, well, we could use cosine, we could use sine to figure out that theta, like the arcs.
Yeah, we could.
Or we could not, and we could use tangent instead, because we've been talking about how tangent is like your slope, and that you can like think about how your x and your y coordinates can relate to one another with your tangent.
Yeah. And also, I think it like if we had used arc sine, we would need to put, what would it be? Opposite over hypotenuse. We would need to figure out the radius first before we find the theta. I think arctan also does a nice job of using what we were given. Arctan of 12 over 5. Because in the next one, we can just do arctan of 5 over -3. I don't know what the radius length is in B yet, but I do know that the angle is going to be arctan of 12 over 5. Sweet. I think that's what it is. Can MATLAB get us that radian measure?
I just got the correction of you can't type in arctan, but you can type in atan.
Oh, I like how MATLAB like tells you what you can't do.
Did you mean? Yeah, I totally meant that. MATLAB, thank you.
If MATLAB can tell you to fix it, why can't they just tell you the answer? Anyways.
It's so that you learn.
I know. All right, 1.17, a little bit more than 57 degrees, which is 1 radian, by the way. I'm going to write rad there just so I don't need to write rad. I'd put a degree symbol if I meant degrees. Boom. So 1.17, that's about that blue angle theta there. And then 13 takes us up to that point. We are in business. Let's do the same thing. So while we do the same thing, what's like the formula for R?
For R, it's the square root of x squared plus y squared.
That's going to give, so we're given the legs of a right triangle. What does that mean about R though?
That r is always going to be our positive value.
So r is allowed to be negative, but in using this conversion formula, we will always get a positive r. So hopefully that doesn't cause any problems. And what do we say the formula for the angle is?
We're saying it's arctan of y over x.
All right, let's see if this formula works. All right, so we should get this point over here in the second quadrant. So the -3 squared is 9. 5 squared is 25. We got the square root of 34. And arctan of 5 over -3, which is, what do you end up getting for that?
Negative 1.0304.
Okay, so that means we're going to go in the negative angle direction, about 57 degrees. Once again, 1 radian is about 57. So we're going to be down here, and then we're going to go, we're getting like this point down here.
Yeah.
This is the coordinate, -34, -1.0304. Why are we getting the wrong answer? What does arctan always output? What is the range of the arctan function?
Is it from negative pi over 2 to positive, negative pi over, negative pi over 2 to pi over 2?
Yeah, negative pi over 2 to pi over 2. So we're always going to get a positive radius, and we're always going to get an angle in the first or fourth quadrant. So this formula that we have come up with will exclusively give us coordinates in the first and fourth quadrant. We're always going to go in the direction of the ray, and the ray will always be in the first and the fourth quadrant. So we need to like fix our formula somehow. What can we do to an asterisk? What can we do to get that correct point? There's two things we can do.
We can either negate our r to flip it over.
Because if we negate the r, then we're in business. This is the point, -√34, comma, -1.03. I'm going to write 0.3 for now. What could we also do?
Or we could like move the theta.
Yeah. How much do we need to move this theta by?
A pi.
Yeah, just pi, right? Boom. So -1.03 plus pi. All right, let's stroll because the next page has the formula. Our radius was right. And then it says when x is positive, when we are in the first or fourth quadrant, arctan will yield the correct angle. But when x is negative, let me not write -x. Let me write x is less than 0. X is greater than 0. When x is less than 0, we are in the second and third quadrant. We're going to need to add pi. We could write a new formula though with a negative r instead, and just always go with the arctan of y over x. Either works. I think a smart thing to do is to graph them in your brain or physically graph them and see if they're like landing on the same spot. Cool. So we got a bunch of formulas.
That's like the pro move for like all math stuff. Like if you're just like kind of confused, then start like drawing a picture. And if you're not able to get yourself to draw a picture, then you need to ask someone for help.
All right, let's do a little bit more and then we're going to be out of here. We got a little bit more to do. I believe actually this is the end. Yep. All right, so we're going to convert not just coordinates now, but equations. So we plotted points, then we plotted equations. Then we converted points. Now let's convert equations. So we have just amassed a bunch of formulas. What are some facts about converting rectangular to polar? I'm gonna write them on the side here.
I mean, we have like some written up on the top. We have the radius is going to be equal to root x squared plus y squared. Is that what you mean?
Yeah, kind of. So like x squared plus y squared. is equal to r. So if I want to convert this to polar, if I see it a roots x squared plus y squared, I can just rewrite it as r.
Mhm.
How about what is x in terms of polar? Do you remember that?
That one is r cosine theta,
Yep. How about y?
r sine theta.
R sine theta, sweet. All right, let's jump over to A. Do you see any of these things that we've written on the right in that equation?
Yeah, we have effectively we have r squared on the
Yeah.
left.
If it helps, you could like square root and then just write r.
Mm-hmm.
But I like the idea of, and I'm actually going to erase it over here. X squared plus y squared equals r squared in polar. So let's replace that r x squared plus y squared with an r squared. We have now converted our x's and y's to polar, and we have the polar equation. Let's go ahead and simplify it.
R is 5.
Yeah.
Or -5.
Or -5, yeah. Both are equivalent to x squared plus y squared equals 25. Right? There's one way to describe the circle in rectangular coordinates that has radius 5 centered at the origin. But there are multiple ways to describe the circle centered at the origin with radius 5 in polar. All right, B. Let's
We have
convert this.
x right there.
Okay, so
R.
x is r cosine theta
Mhm.
equals 4. And we could stop there, but this is actually a good moment for me to once again justify why it irks me that we go r comma theta. But in general, when we're writing the equations for shapes in polar, we have r as a function of theta. R as a function of theta. So let's isolate the r like we do when we have y as a function of x. Let's get the r by itself so that you give me a theta, I give you an r. You give me a theta, I give you an r. And we construct the picture. So what is r here?
R is 4 over cosine theta, or 4 times, is that secant?
Yeah. And actually, fun fact, the vertical line in polar. Remember when we did theta equals pi over 4? It wasn't a vertical line. It was a line going through the pole. The vertical lines in polar, you write as secant theta. R equals 4 secant theta. If we actually, this is a good moment to do this as well. Let's jump over to Desmos. Beautiful, Freeman.
Desmos. You're doing the most.
I really am. So if I hit theta here, Theta, it actually assumes polar. Desmos is pretty smart. But if you want to make sure that it's assuming polar, you can jump over to polar mode right here. Ooh.
It's pretty cool.
It is. Let's so here we are. R equals 4 secant theta is the vertical line. Right? If I type in r equals 4, that is 4 equals 4, which is true. I'm struggling with my keyboard right now. R equals 4, we get the circle. So Desmos is pretty smart in that it recognizes polar equations. Let's jump back over here. Boom, 4 secant theta is the vertical line that this number right here units away from the pole. What do you think r equals 4 cosecant theta is going to be?
Horizontal line?
Horizontal line.
Yes.
All right, let's start. Oh, what a crab!
Yep.
Like it's a normal crabbing, the verb, but that crab, like literally, is an intense looking crab. Yep. You're making it crawl. Do you? It's amazing. Yep. I like you're making it crawl like a crab crawls up and down sporadically. All right, write the polar equation below in rectangular form.
Oh, we did that one before.
We did do this one before, but I want you to think about this algebraically rather than geometrically. So we could just graph it, look at it, and be like, y equals x. But on the side here, how do I convert from polar to rectangular? What is theta equal to?
Arctan of y over x.
Y over x, sweet. And then what is r equal to?
The same thing we had before.
Yeah. R equals x squared plus y squared. So wherever we see an r, we can replace it with an x squared plus y squared. And wherever we, well, not true. Wherever we see an r squared, wherever we see an r, we can replace it with the square root of x squared plus y squared. And wherever we see a theta, we can replace it with arctan. So let's do that here. Arctan of y over x equals pi over 4. Let's simplify this a little bit. How can I get rid of that arctan?
Take tangent on both sides and then I guess chop.
Oh.
Do we say that? Or
I don't know. Tan.
tan.
Can you do the tan?
No. All right, so do some laser swords.
I've been watching a lot of Clone Wars, by the way.
Oh, me too.
I know. I'm in season 5.
Oh wow. No, I'm in season 1.
I went from season 2 to season 5 in the span of 2 weeks. It was kind of a problem, but
wow. That's really
y over x equals tan of pi over 4. That's 1.
1. Right.
Let's multiply by x on both sides. And we got what you intuitively knew from graphing, because drawing a picture is really just the best way to do all math, in my opinion. All right, B, r equals 5 sine theta. What do you want to do here?
We can just start like replacing stuff.
Yeah, well, so I guess we could replace that sine theta with the theta with arctan y over x.
Wow.
That sounds like we're getting like embedded trig functions. I don't want to do that. Hey, what is r cosine theta and r sine theta in
Those
rectangular?
are x and y.
X and y. Can you get an r sine theta here?
No. Yeah.
What could you do to have this? Not that, this. We're like really close to it, right?
Mm-hmm.
I'm going to multiply by r on both sides.
So then you get r squared.
I get r. What's r squared?
X squared plus y squared. Oh, that's nice.
Boom. Equals 5 y. Boom. Do you know what that is?
No.
I'm going to take you through a real quick geometry lesson. I'm going to subtract that 5y.
Okay.
Now we're equal to 0.
Mm-hmm.
And I'm going to complete the square in y. I'm going to divide -5 by 2, -5 halves, square it, 25 fourths. Add that to both sides. And then now I got a perfect square, trinomial, y minus 5 halves squared equals 25 fourths. Does that look familiar?
Yes.
That
it looks like a circle that's centered somewhere else.
Yeah, centered at
Not
the
the
x coordinate is 0, and the y coordinate is going to be, so it's x minus h. H is your center, your x coordinate of your center. Y minus k is the y coordinate. And then we get 5 halves squared. That's our radius.
Wow.
This is a circle centered at 5 halves, 0, 5 halves with radius 5 halves. Let's graph it in Desmos. R equals, I did it again. R equals, what was it? It was 5 sine theta.
Look at that.
Look at that. 2.5 right there, 5 halves is our center. And its radius is, once again, also 2.5 because it gets us down to the origin. Okay. If I type in this, x squared plus y minus, what was it, 5 halves? Squared is equal to 25 fourths. I get the same thing. There you go.
Very cool.
Yeah, so we multiplied by r there to get r sine theta. And then really, you can stop here. But I mean, if you're a little bit extra, you can always complete the square like people did in geometry all the time. And then identify more elements of the circle. But when you see an x squared and a y squared, it's usually a circle or another conic section. X squared minus y squared is going to be a hyperbola. If you change the coefficients, you're going to get an ellipse. And if you get rid of one of the squares, you're going to get a parabola. Boom. There we go. That is our intro to polar coordinates lesson. The goal here is to be able to graph polar coordinates and to graph polar equations, and then to be able to move back and forth between what we used to know, rectangular, and what we know now, polar. Let me go ahead and stop this share. Boom. Any words of wisdom? Any
my mind is going blank. I feel like it's really nice to garden. Like,
ooh.
it's
I
like
miss
really
gardening
nice.
so much.
And it's really nice to eat food that you grew. Like, it's tastier.
It really is. Have you ever grown tomatoes and then eaten those tomatoes?
And then it's like all the other tomatoes are trash.
All the other tomatoes in the world are trash. Oh my gosh. If you buy a tomato from the grocery store, it tastes like water. If you grow your own tomato, it tastes like, the only way to describe it is a tomato, because it's such a unique, delicious flavor. Oh my, I miss growing tomatoes so much. I just don't have the ability to in an apartment that I live in currently. I just need to find a new apartment with a balcony. That's what I need to do.
Or you could just like sneakily just like put some tomatoes on the balcony that's by Mr. Street's classroom.
I could. I could grow my own tomatoes at school. Ooh, that's a great idea.
Because like that's what Hortz does, the horticulture class. That's where they grow stuff.
Yeah.
It's great.
What was I gonna say? We were going to try to find a community garden, but then COVID happened. So we put that idea on hold. All right. My mind's blank. So let's just like bask in that word of wisdom. I forget what you said though. Explicit. Like, was it garden? More.
It's nice to garden.
It's nice to garden. I like that. Cool. Let's go ahead and close this one out.
Okay.